Welcome to qnawire.
All right, so today we're going to look at E. coli. E. coli doubles every 20 minutes. In this example, that's fast. We're going to work with hours, so that's actually 1/3 of an hour. 60 minutes, right, divided by 20 gives me 1/3. Okay, we know that we start off with 50 cells of E. coli, and in general, for exponential growth, we have this form, P, where P is going to be our number of cells of E. coli. P of t is equal to P at 0, E to the KT. We have already information that we start at 50, so I can go ahead and plug that in. But I still don't know K, so I need to solve for K. So I'm going to use this info that E. coli doubles every 1/3 hour to solve for K. All right, so if we double, that means we're at 100 cells. And that is when T is 1/3. So we want to solve for K. So let's go ahead and divide both sides by 50. And whoops. No, we're good. Okay. And then we'll do ln of both sides. So ln of 2, ln of e to the 1/3 K is just 1/3 K, because inverse composite functions unravel each other mathematically, and we just get our exponent out. And then I can cross multiply or just multiply both sides by 3. K is then 3 ln of 2. I'm going to switch sides. And if I want, I can bring that exponent, do a little log rule. That exponent or that multiplier of 3 can become an exponent. So K is actually natural log of 8. All right, so that's going to be helpful. Anyway, that is our K value. And so that's part A. Okay, so part B now, we are going to find our general formula. So P of t, now that we know K, our general formula is 50 e to the ln of 8 times t. And I can manipulate this. I have a t multiplier, so if I rewrite it as t ln of 8, that t can become an exponent. So I get 50 e to the ln 8 to the t. But again, inverse composite functions, out pops the argument. So P of t can be rewritten as 50 times 8 to the t. And both of these are fine ways to write it. Just two different ways to write our formula. Great. Okay, let's do part C. Part C now, we are interested to know the population of E. coli after 6 hours. So we're going to plug in 50 times 8 to the 6. And this is in units of cells. And when we plug that in, we get a really huge number of 13,107,200 cells. So that is really rapid growth. No thank you on the E. coli. Okay, so next we are going to find the derivative of our population with time. So we could use either form, but I'm going to go ahead and just use the second form here. So 50 goes along for the ride when I take a derivative of an exponent function, or exponential function. It looks like itself times the natural log of the base. So that is our rate of change of cells of E. coli with time. If I want to know what it is at 6 hours, I'm going to go ahead and plug in 6 for t. This, by the way, is in cells per hour. And we end up, if we plug that in our calculator, once again, it's cells per hour. And we get, hold on, let me just fix this, per hour. Whoops. Okay, so if we plug that in our calculator, we get this huge amount, a really big rate of growth, really crazy big. Okay, so that is our rate of growth in cells per hour. So really, really big growth. Okay, so last part now, we are going to, let's change colors. Let's do part E. Now we are going to figure out how long it takes to get to 1 million cells. So we're going to set our function, which is whoops, let's fix that. Our P of T, which is 50 e to the ln of 8. Oh, actually, I'll use the second one. Never mind. We have two forms. Let's use the easier one. Okay, so 50 times 8 to the t. We need to make that equal to 1 million cells, and we're basically just going to solve for t. So we're going to divide through by 50, and that will give us 20,000 cells. Then we are going to, we want to do the inverse operation. So that is, if I do log base 8 of both sides, then I will get t to pop out. So t is log base 8 of 20,000, which you can do, use another log rule and do ln of 20,000 over ln of 8. Very useful log rule. And when we plug that in our calculator, we get 4.76 hours to reach 1 million cells. Woo! Okay, hopefully you enjoyed that. Have a wonderful day.